Hi, I'm Sam Narenberg, and today I'll be talking to you about our project, Imaging Through the Body. So, the goal is to look inside the body, and specifically the brain, using only light. And so, as you can see here at the slide, as we shine light through the skull, it is scattered, and we cannot make out any details of objects inside the skull or behind it. And imaging through scatter medium like the skull becomes more difficult as the medium gets thicker. And to date, there are no techniques capable of imaging through 100 scattering lengths, which is approximately the thickness of the brain, which we'd like to image inside. So our research is developing such technique. We're solving the problem by using SPAD cameras, and SPAD cameras collect the arrival time of photons in addition to their spatial location. So this figure illustrates our method. So on the left, we have pulsed laser light incident on an object which is embedded in a scattering medium. And here the object is given by an A, but in a real life application, it would be something like the blood vessels inside the brain. So the photons which exit the scattering medium are detected by a SPAD camera. And this gives us a series of time histograms. And these time histograms allow us to distinguish between different paths taken by photons through the medium. These paths contain information about the object's shape. So passing the two pieces of information, the spatial distribution of light and the time histograms, to a computer, we are able to reconstruct an image of the object through a very thick scattering medium. So some results, we can see from this figure on the left that as we increase the time resolution, as shown on the bottom rows, from 1,000 picoseconds to 55 picoseconds, while keeping the spatial resolution of the detector fixed, we can go from a complete blur to being able to distinguish two parallel lines with millimetric precision through more than 80 scattering lengths. And this resolution that we've demonstrated in a lab environment rivals MRI. So we're very interested in your input as to end uses, but these are some applications that we've been thinking about. We want to be able to identify and classify different types of strokes. So if a stroke is ischemic or hemorrhagic, they have two very different treatments, and giving the wrong treatment can exacerbate the effects of one of the strokes. So being able to identify them and classify them quickly is extremely important for patient outcomes. And similar methods can be used to identify subdural hematomas. We hope that our research will eventually yield portable or wearable brain scanning technology. And this would allow it to be deployable by first responders at the scene of an incident or by individuals who want to or need to self-monitor. And from a research perspective, it would be convenient for neuroscience studies that want to examine the effect of motor and visual stimuli without confining subjects to a MRI machine. So these are the researchers who are currently associated with the project. And if you would like to contact us, please do so at the email here at the bottom, which is the principal investigator, Daniele Faccio's email. Thank you very much.